Hello and welcome. Now that we know a bit more about waveforms, it's time to talk about the architecture of a synthesizer. The synthesizer contains modules where we can make good use of those waveforms. Usually built with three main components: oscillator, filter, and amplifier. These components are the core base of the signal of the synth, the part we can actually hear. Then we have other set of components which act like modifiers or controllers: envelope, LFO, even the keyboard. They can usually be assigned to any part of the synth or to a specific part and modify it, control it, be it to induce movement on a previous static sound or to change the way it responds to the way we play. The oscillator generates a continuous sound wave, and its main parameters are usually the waveform and pitch, or frequency. The waveform is where we choose the type of signal which is being generated by the oscillator. We usually have the basic waveforms to work with: sine, triangle, saw, square, and we also can have a noise generator. That will dictate the harmonic content and therefore the timbre of our sound. As we previously seen on waveforms video, the type of waveform defines the harmonic content by using more or less harmonics related to the fundamental. A sine wave only has a fundamental tone and no harmonics, so there isn't much to filter out when it reaches a filter. While a saw wave is extremely rich in harmonics with a lot of high-end frequencies. The pitch, or frequency, defines the speed at which the oscillator is generating the waveform. While pitch is given in musical notes or intervals, frequency is given in hertz, which means how many cycles per second we have from that waveform. The filter, as the name implies, filters out part of the signal which is coming from the oscillator. Main parameters are usually the filter type, cutoff, and resonance. The filter type defines which frequencies above, below, or around the cutoff point are to be removed. A low-pass filter will remove frequencies above the cutoff, while a high-pass filter will remove the ones below. A band-pass filter will let the frequencies around the cutoff point to pass through, filtering out the rest above and below. A band-reject filter, also known as notch filter, will do exactly the opposite by cutting off the frequencies in and around the cutoff, letting the above and below frequencies to pass through. Depending on the synthesizer, filter types can have a number attached to their name: 6, 12, 18, 24. This means decibels and filter slope. It can be seen at how hard it is the cutting of the frequencies: 6 dB per octave, 12 dB per octave, 18, 24. With a low pass 12 at 1 kHz, all frequencies below will pass through, and the frequencies above will decrease 12 dB per octave, meaning that the signal at 2 kHz, 1 octave higher, will be 12 decibels lower in amplitude, while at 4 kHz, 2 octaves higher, 24 decibels lower, etc. The cutoff is given in hertz and is the point where the filter starts to act. The resonance is the accentuation or boost of the frequencies at the cutoff point. It serves really well the purpose of emphasizing what the filter is doing, particularly when we have it modulated up and down, and it can also be the width of the band reject filter band. Filters act much as an EQ, but the big difference is that the filter sometimes helps printing the signature of a sound, particularly when we talk about old analog synths, where a specific component is inducing a specific characteristic on the electrical signal, making it different from the others, therefore printing a different and unique color. That's why the same waveform with the same filter type and slope can sound different on two different synthesizers, because the oscillator and filter components have their own signature. The amplifier, there's not much to say apart from it controls the volume of the signal. But that leads us to the next subject, which is the modulation. Controlling the amp or volume, we have the envelope generator, or ADSR envelope, usually with 4 points, known as attack, decay, sustain, and release. This defines how the volume of the amp will behave over time, whenever a key is pressed or the synth receives a note from the sequencer. Attack is the first point of the envelope and controls how much time it takes to reach the full volume. Decay controls the time from full volume to the sustain level. Sustain is the static level at which the sound will stay while we hold the key pressed. And release is the time it takes to go from sustain level to silence when we release the key. But we can have more than one envelope on a synthesizer, and we can assign them to any other of the synth functions to have the same overtime behavior on that chosen parameter. Let's see it on the filter, for example. The other main component of modulation is the LFO, or low frequency oscillator. It's basically like a regular oscillator generating a waveform signal, only that the frequency is so low that doesn't even reach the minimum 20 cycles per second needed to be heard by our ears. It is therefore routed or assigned to other function of the synth in order to print that continuous waveform in a changing pattern of the chosen parameter. This can be helpful to mimic tremolo and vibrato effects of acoustic instruments, to introduce movement on a static sound, or simply to go creatively wild by experimenting different modulation approaches and destinations. The main parameters of the LFO component are the waveform and rate, or frequency. The waveform, like in general oscillator, will let us choose a waveform, which will translate, in this case, in the modulation values. In many modern software synthesizers, we can actually draw our own waveform. The rate determines the frequency of the speed of the waveform. It's usually given in Hertz, but many modern synthesizers have a sync option that lets us control the rate according to musical values, like 1 or 2 cycles per bar. That is extremely helpful when we want to relate the modulation with the BPM of our music. These are the basic components and architecture of a subtractive synthesizer, one of the most common types of synthesis we work with. Knowing these principles puts us much more comfortable to explore this and other types, which is what we're going to do in the next video, briefly covering the most common ones.